Hello everyone, my name is Srinivas. I am currently a PhD student at Aries Nainital and I am working under the supervision of Dr. Jeevan Pandey. First of all, I would like to thank the organizers for giving me this opportunity to present this talk. Now, the title of my presentation is Change in Accretion Flow in the Intermediate Polar V709 Cas. Can you switch to the content slide?
Okay.
So here are the contents of my presentation. First, I will give a brief introduction. Then I will move to the data part from where we have collected the data. Then I will present the analysis and the results of it. In analysis, we have basically done three things. That is, first we have done the periodogram analysis, then the evolution of the spin and beat pulses, then the pulse fraction, and finally then we will move on to the conclusions. Next slide.
Okay.
As many of the previous speakers have explained about the cataclysmic variables, so I am not really going very into the depth of it. I just wanted to say that on the basis of magnetic field, it is divided into non-magnetic cataclysmic variables and magnetic cataclysmic variables. Magnetic is further divided into polars and intermediate polars, and my work is basically related to intermediate polars. Next slide, please.
Okay.
Okay. So intermediate polars are magnetic field in the range of 1 to 10 megagauss. Now these are asynchronous systems, that is they have different orbital and spin periods unlike the polars, and these are oblique rotators, that is the magnetic axis and spin axis are not aligned with each other, and in this case there are three possible accretion mechanisms. Can you just switch to the transition? Okay, so the first one is the disk fed accretion. Now in disk fed accretion, what happens is that matter is accreted from the inner edge of the disk, that is where the magnetosphere disrupts the disk. Now this can be identified if modulation is observed at the spin frequency. Can you switch to the next slide?
Okay.
The next accretion mechanism is the stream fed accretion. Now in stream fed accretion, what happens is that the magnetic field is so high that disk is unable to form and the matter is accreted directly via the stream. Now this can be identified if modulation is observed at the beat frequency. By beat frequency, I mean it is basically the spin minus orbital frequency. Can you just click on to the next?
Okay.
The next is the disk overflow accretion. So the disk overflow accretion is that there is already a disk fed mechanism going on, but what happens is that some of the material just skims over the disk and directly hits the magnetosphere. So it's like both of the previous modes of accretion are going on at the same time in this mode of accretion. Now this can be identified if modulation is observed at both beat frequency and also at the spin frequency. Can you switch to the next slide?
Okay.
Now, our object of interest is V709 Cas, which is a well-known intermediate polar. This was first recognized by Habel and Moch from the Rosat All-Sky survey. They found the spin period to be 312.8 seconds, but they were confused about the orbital period. They said that the orbital period can be either 5.4 hours or 4.45 hours. But a more precise calculation of spin period was done later by Norton, and he set the spin period as 312.78 seconds. He also suggested that this is a disk-fed accretor system. The first evidence of beat was reported by Koshevnikov, and he reported the beat period to be as 317.94 seconds. Now with this, the confusion with the orbital period was also cleared with the earlier calculated spin period, and from his newly found beat period, he said that the orbital period should be in the range of 5.28 to 5.43 hours. But even more precise, accurate orbital period were given by Thorensten using the radial velocity spectroscopy. Now, for this project, we have used the data from the Transiting Exoplanet Survey Satellite TESS. Now, the advantage with TESS is that we can get a very long and uninterrupted data. Now, we wish to use this long and uninterrupted data to probe the accretion geometry of this V709 Cas. and we also wish to find more precise orbital spin and other sideband periods. Can you switch to the next slide?
Okay.
Okay. So as I already mentioned, we have taken the data from the TESS, which takes it from the optical band. Now the observations of TESS are generally broken up into sectors, which like each sector is having a field of view of around 24 degree cross 24 degree, and each sector nearly lasts for around 27.4 days. Can you just press enter so the table pops up?
Okay, next slide.
No, the table. Okay. So as you can see in the table that we have uh, data from 5 sectors, that is 17, 18, 24, 57 and 58. The 17, 18, 24 are nearly little bit old data, that is it was around 2019 and 20, whereas sector 57 and sector 58 are pretty new, that is they were observed in October and November of the previous year. Can you switch to the next slide?
Okay.
Okay, just press enter when I say.
I think we see the
So,
whole slide of analysis and results.
okay, so just you are seeing the light curve box, right?
Yeah.
Okay, so first as usual, we do the light curve analysis, uh, then just press enter. Just keep on pressing enter, I'm seeing it. Okay, then we do the power spectra analysis using the Lom's-Cargill periodogram. From the Lom's-Cargill periodogram, we identify different periods. Using these periods, what we do is that we do phase folding around those periods, and we do the 1 day phase folding around those periods. Why we do 1 day phase folding, I will say it in a couple of while. And then using the information from the phase folded light curves, we do the pulse fraction plot. Can you see the light curve?
Yes, we do.
Okay, so this is the light curve of V709 Cas. As you can see, this consists the data of 5 sectors, but you cannot see properly the variability of it. So if I zoom in, just press enter.
Yeah, I think we're already zoomed
Okay.
in. Yeah.
Okay, so we can see the data of sector 17, which is one of the sectors, and if we zoom in further, we see that there is variability on a day by scale. What these 3 plots you are seeing is that you are seeing variability on a day by scale. So this is what motivated us to do a 1 day analysis of this V709 case. Can you switch to the next slide?
Okay.
Next, we have done the power spectra analysis. First, at the moment when we started the project, we had data of only sectors 17, 18, and 24. And in this sector, the frequencies which we have obtained is marked in the dashed red vertical lines. We get the orbital, spin, and the beat frequency in all the 3 sectors. And when we analyzed the data of sector 57 and sector 58, we also got orbital, spin, and beat frequencies. But there is a slight difference between these 2 new data and the previously obtained data. The difference lies in the power of the spin and the beat frequency. That is, as you might see in sector 17 and 18, the powers of the spin and beat frequencies are almost comparable. That is, there is not much difference, but the spin frequency being slightly dominant over the beat frequency. But when you see sector 57 and sector 58, the power of the spin frequency has increased very much, and while that of the beat frequency has decreased. In fact, it has decreased so much that it has gone below the significant level. So there is change occurring in the system within a span of 2 to 3 years. Can you switch to the next slide?
Okay.
So these are the plots which I showed earlier in the previous slide. Now this is the combined plot. Now this is the combined sector plot. In the combined sector also we are able to see the orbital, beat and the spin frequency. In the table mentioned in the right hand side, you can see we have found out all the orbital periods, spin period and beat period in all the individual sectors and also of the combined sector. And the results are fairly consistent in almost all the sectors. These obtained periods, that is orbital spin and beat periods, are in agreement with the earlier obtained results. Now in the power spectra, as you can see, we have obtained the spin frequency and beat frequency in all the sectors. So we can say that this is a disk overflow system. But we may also note that the power of the spin frequency is more than that of the beat frequency in nearly all the sectors. So we can safely assume and say that the accretion of this system is the disk overflow with disk fed dominance. Can you switch to the next slide?
Okay.
Okay. So from the Lom's-Kaggle periodogram, we basically obtained different periods, and we also probed the accretion geometry to be a disk overflow with disk fed dominance. Now next we move to the one-day phase folded light curves. In one-day phase folding, we did phase folding around the spin period and the beat period. We have used the notion of normalized flux, which is just the ratio of the flux to that of the mean flux. Can you switch to the next slide?
Okay.
So this plot represents the spin phase folded light curve of sector 17. Now I have zoomed in the plot of couple of disks. We have done individual analysis, so I've zoomed in a couple of disks just for clear visualization. Now as you can see on the left hand side, the day 8 and day 18, we see a double peaked pulse profile. Now what this double peaked pulse profile really means is that that accretion is happening onto both the poles, or what we know as that V709 Cas is a two pole accretor. Can you switch to the next one?
Okay. And you have 2 minutes remaining.
Okay, sure. These are the plots for sector 18 and sector 24. This literally shows the same thing, that is we have a double peak pulse profile in all the days. To the next slide.
Okay.
This is the plot for sector 57 and sector 58. This sector also follows the same trend as that of the previous three sectors. Okay, to the next slide.
Okay.
Okay, so long story short, what we got is that from the spin phase folded light curve, we get a double peak pulse profile, and from the double peak pulse profile, we infer that it is a two pole accretor. Now from this phase folded light curves, we calculate the pulse fraction for each day, and we plot the pulse fraction plot. To the next slide.
Okay.
Okay. So this figure represents the spin pulse fraction plot. On the left top side, you can see that of the sector 17 and 18. On the right hand side is of sector 24, and on the bottom left hand side is of sector 57 and 58. What we see from this plot is that the spin pulse fraction is not the same. It is varying on a day-wise basis. That is, someday it goes on increasing, then again decreases, like that it keeps on varying. Can you switch to the next slide?
Okay.
Okay. We have also plotted the pulse fraction for the beat phase, and the beat pulse fraction is also varying on a day-wise basis. So what this varying pulse fraction means is that the amount of accreting material is not constant, it is varying. Like if beat pulse fraction is varying, it means that the amount of material accreting via stream fed mechanism is varying. So on the basis of this varying pulse fraction, we say that the amount of accreting material is varying in V709 Cas. And also we say that the beat pulse fraction is smaller than the spin pulse fraction. This indicates that more amount of material is accreted via disk fed mechanism. This further strengthens our claim that V709 Cas is a disk overflow with disk fed dominance. Let's switch to the next slide. Can you switch to the next slide?
Yeah, it's your conclusion slide.
Yeah, this is the last slide. Okay. So what we learned is that from the power spectral analysis, we found out the orbital spin and the beat periods, and from it we also probed that the accretion geometry is a disk overflow with disk predominance. Now from the spin phase folded light curves, we saw that it has a double peaked pulse profile, which inferred that it is a two-pole accretor. And from the pulse fraction plot, we said that the amount of accreting material is varying. Okay. And that's all from my side. Thank you.
Great, thank you very much.